Now I will talk about the p-value and how it can be used for two-sided test. So basically, the p-value is the probability of obtaining a test statistic such as sample mean or z-square that is at least as extreme as the one observed, assuming that the null hypothesis is true. In other words, the p-value helps you quantify the likelihood that the data could occur under the assumption that null hypothesis is correct. If we have a smaller p-value, it suggests that we have a stronger evidence against the null hypothesis. So how is it calculated? So basically the p-value is derived from the test statistic. A test statistic can be either thing like the z-score, which measures how far the observed data is from the null hypothesis. So based on the test statistic, we calculate the p-value by finding the probability of the data, which would be at least as extreme, assuming that the null hypothesis is true. So how do we interpret the p-value? So p-value basically provides a quantitative measure about the strength of the data evidence against the null hypothesis. So if you have a very small p-value of less than 0.05, it suggests a very strong evidence against the null hypothesis. The result is therefore consistent, statistically significant, and we thus reject the null hypothesis, suggesting the observed effect is unlikely to have any effect because of any random chance alone. But if we have p-value greater than or equal to 0.05, it suggests a weak evidence against the null hypothesis, and in this case the result is not statistically significant and we fail to reject the null hypothesis in this case, meaning that the data which are consistent with the assumptions that null hypothesis is true. So we can do a two-sided test which is done to see whether the sample mean is significantly different from the hypothesized population mean. So it can be either higher or lower than that value. So in this case, two-sided test, the p-value is calculated from distribution trail from both the sides. Now let's look at the code regarding the p-value for the two-sided test. So these are for the importing the libraries. Next, this is a statistical data visualization built in top of Matplotlib, Seaborn. Uh, the next lines here n sample is the number of random sample generated for the simulation. In this case, it's 1000. And small is the sample size for each random sample. Each sample contains 10 data points. Mu is the population mean, which is set to 100 in this case, and sigma we have set to 10 here. Mu naught is the mean for null hypothesis. Next, we have the value. We set the p-values to be 0, and we initialize an array to store the p-value each for 100 sample. Initially, it is filled with all 0 values. Next, we have the for loop, which it iterates for n sample. Here which is 1000, so it will iterate 1000 times. So each time it generate a random sample, and we calculate the p-value. And from this line, we generate n random data points, here 10 in this case, from a normal distribution with the specified population mean and the standard deviation. And in this line, we convert the sample x into pandas data frame, and then we compute the mean of the sample. Since this is a single column data frame, we have used axis is equal to 0 to compute the mean across the rows. Next, we calculate the z-score for the sample. The z-score tells how many standard errors the sample mean is away from the null hypothesis mean, and then we compute the two-tail p-value for the z-score. So basically, the stats norm.cdf gives the cumulative distribution function of the standard normal distribution, and then multiplying by 2 accounts for both the tails of the distribution, that is for a two-sided test. And here we convert the p-value arrays into pandas data frame for make it easier to plot. And then these are for plotting the histogram. So if we run this, so now let's suppose take a condition in which the null hypothesis is equal to the population mean. Here mu naught is the null hypothesis and is the population mean. So if we have both the values to be same, if we run it, you will get a distribution like this. Okay. So basically, so this is a standard calculation to test the effect. So basically, it tests the sample mean if it's different from the population mean. So now let's check it for some other conditions also. Let us check it for this one. We set the null hypothesis to be slightly greater than the population mean. Okay. So if we run again, so we will get this value. Okay. So basically, you can see that if we set the sample mean to be significant different from the value, that means it is further away from the population mean. So basically, this provides the evidence that the sample might be different from the mean, that is notably higher from the population mean. So basically, this approach is useful when you have a specific alternate hypothesis that the true mean might be quite different from the population mean. So we can do it for other case as well. So if we run it, we can see that it is intermediate of those two extreme values. So in this case, the population mean is only, sorry, the null hypothesis is only slightly greater than the population mean.